All right, welcome everyone to our final lesson on trigonometry. We are going to be moving up. That's not 100% true. We will be using trigonometry a lot, but this is our final lesson in our trigonometry unit, Unit 6. We're going to be moving on to some new stuff after this. Today we are going to learn our final set of formulas, the sum of sinusoids, specifically some formulas called the sum to product and the product to sum formulas. And they're going to make solving easier, but I want to get it out of the way now. The essence of this lesson isn't to give you another tool. It's to show the tools that we have been amassing for the past month. We can pull out and then create new tools with. And that's kind of the essence of math in general. It's learning some tricks here and there, some fundamentals, and then being able to do really cool mathematical things with those tools. It's kind of like painting a picture. You learn basic strokes, and the next thing you know, you can make a beautiful picture. And that's kind of what we're going to do today. We're going to use what we know to do some really cool things. All right, so to do that, we have an equation that you have solved before. Cosine x is equal to 1 plus sine x. And I want you to think for a second, how have you solved this before? This might be a good time to pause the video and try to solve it with the tools that you have and come back to solve this with me in a new way. All right, so if you solved it, awesome. If you didn't, that's okay as well. If you solved it, great, got some extra practice. Hopefully, it was grueling and tiresome and frankly bothersome. Hopefully, the way we're about to do it is way more elegant. So we're going to use the tools that we have, but in a really cool way. And that's the essence of this video, using the tools that we have in new, interesting ways. Okay, so normally, you'd square both sides. You get cosine squared is equal to 1 plus 2 sine x plus sine squared x. You've now squared, so you've created extraneous solutions potentially. And if you solved this, you did. But I'm going to do something different. I'm going to move that sine to the other side. Cosine x minus sine x equals 1. And I'm going to do something that honestly, as a student of mathematics myself, I would never think to do. But it's going to make you rethink how you've solved every trig equation up until now. You're going to rethink about, did I do it the best way? I'm going to multiply through by root 2 over 2. Watch this. I'm going to multiply the left and the right-hand side by root 2 over 2. All right, think about why I'm doing this as I write it out. Root 2 over 2 cosine x minus root 2 over 2 sine x is equal to root 2 over 2. Now, root 2 over 2 is one of our special angles. Sorry, it's not one of our special angles. It is the coordinate, specifically the x and the y coordinate, of pi over 4. Pi over 4 radians on the unit circle. Now think about what can you do to simplify this further. Root 2 over 2, pi over 4. The cosine of pi over 4 is root 2 over 2. The sine of pi over 4 is root 2 over 2. I have root 2 over 2's in my equation. I'm going to replace the root 2 over 2's with cosine pi over 4 and sine pi over 4. Cosine pi over 4. I'm going to replace this root 2 over 2 with sine pi over 4. Why did I do that? I'm going to pause once again to give you a second to think about why I might have done that. cosine, cosine, sine, sine, sine. Cosine, cosine, sine, 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 sine. I can turn this into a cosine sum formula. Cosine of pi over 4 plus x. Cosine, cosine, sine, sine, sine. I'm using the original identity that we derived on the unit circle in reverse. We've done this before in some practice problems. Right? Cosine, cosine, sine, sine, sine. Now I have cosine pi over 4 plus x is equal to root 2 over 2. And I have eliminated one of my trig functions. I no longer have to square. Cosine, cosine, sine, sine, sine. When is cosine root 2 over 2? Well, we already established that. That's pi over 4. But also, it's root 2 over 2 at 7 pi over 4, right? Or negative pi over 4. That's what I'm going to choose. Pi over 4 plus x is equal to pi over 4 and negative pi over 4 plus 2 pi k. Subtract that pi over 4. And we get negative pi over 4 plus or minus pi over 4 plus 2 pi k. And that is our final answer. No extraneous solutions. We never squared. We never produced any answers that wouldn't necessarily be true. Negative pi over 4 plus or minus pi over 4 plus 2 pi k. In other words, 0 or negative pi over 2 plus 2 pi k each. But there you go. All right, today's lesson is not about learning new tools necessarily. It's about using the tools that we have to do problems more beautifully, frankly. We can do this trick with any cosine and sine. So I have a different problem right here. Now we have a 3 and a 4 as coefficients instead of a 1 and a 1 as I had up here. A 1 and a negative 1. We have a 3 and a 4. So we need to think, how can we use the same tool, the same trick, to produce a cosine, cosine, sine, 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 or a sine, cosine, cosine, sine? That would have worked as well. We could have easily had done that in the previous one. All right, we have 3 and 4. And we can't just multiply by root 2 over 2 here, because then we'll have a 3 root 2 over 2 and a 4 root 2 over 2, which is not on the unit circle. All right, but is there an angle on the unit circle that produces something with a 3 in it and produces something with a 4 in it? Here's the beauty. If I multiply in this problem by 1/5, why am I doing 1/5? Think about that for a second. 3/5? Where am I getting that 1/5? That's another question. Right, that 3/5, that 4/5, the reason why I multiply by 1/5 is because I can construct a triangle on the unit circle that has legs 3/5 and 4/5. 5 is that perfect hypotenuse for 3, 4, and 5. 3, 4, 5. In order to figure out what you need to multiply by to use this tool, you need to figure out what the hypotenuse of a 3, 4 triangle is. If I had different numbers, if I had a 1 and a 7 here, I would need to figure out what is the hypotenuse of a triangle with legs 1 and 7. That'd be root 50. So I'd multiply by 1 over root 50. And then I would have the same situation over here. I would have a triangle that is factual, satisfies the Pythagorean theorem, and is on the unit circle, and then gives me a cosine, whatever this angle is, of 3/5. And it gives me a sine of 4/5. That is what you need to multiply by. And then we can proceed. This angle right here, it is just the arc tan of 4 over 3. It's also equal to the arc sine of Or would that be 4/5? The arc cosine of 3/5. There's lots of the arc cosecant of 5/4. The arc secant of 5/3. The arc cotan of, what would it be, 3/4. You can use any of these. I'm going to use the arctan one. But that's what the angle is. It's just a number. We don't know what it is in our heads, but the calculator could easily tell us. And then we proceed. 3/5 is the the cosine of the arctan of 4/3. Cosine 2x minus the sine of arctan of 4/3. Right, that would give me 4/5. Here's the triangle with arctan 4/3. The sine of it is 4/5. Boom. And then we have cosine, cosine, sine, sine, sine once again. Cosine of, cosine of the arctan of 4/3. That is an angle. It's just theta. I could be writing theta this whole time to save myself some trouble. Cosine, cosine, sine, sine, 2x equals 1/5. And then I proceed like I did before, right? 2x, I'll write it anyways. Arctan of 4/3 plus 2x is equal to the arc, and I need to actually kind of double it up. The arc sine, the arc cosine of 1/5 plus 2 pi k, and the negative arc cosine of 1/5 plus 2 pi k. Subtract the arctan of 4/3, divide by 2, you got yourself an answer. I'm going to go ahead and write it. Arc, I'm going to have the negative arctan of 4/3 divided by 2 plus the arc cosine of 1/5 divided by 2 plus pi k. And I shouldn't have written, nope, that's correct. And the negative arctan of 4/3 divided by 2 minus arc cosine of 1/5 divided by 2 plus pi k. I probably could have written it in a more fancy way, but I didn't. All right, sorry for drawing out those two problems. But I wanted to show you, once again, the theme of this lesson, using the tools that we have to do things more elegantly. Not necessarily to memorize new tricks, but to show you that what we've learned is just scratching the surface of how we can use those tools. I'll try not to berate you all with analogies that are fairly meaningless. All right. I got a little bit more in here for you. And I've actually solved this problem with a few people in class. Cosine 2x plus cosine 3x is equal to 0. But once again, the theme here is solving things more elegantly. Think about how we did this in class, and think about how maybe we can do it in a better way. Now, once again, as a student of mathematics, I would have never thought to do it this way, but I just feel, I feel a little bit more intelligent because I've been shown this way. It's a very beautiful way to solve this problem. So normally, we would use the double angle formula. Cosine squared x minus sine squared x. One of the three cosine double angle formulas. We'd then break up the 3x into an x plus a 2x. That's going to start getting pretty hairy. We'd break up the cosine 2x into something bigger. We get this mess. It solves eventually, but it's a lot of work, and it's just not a good time. There's a more cool way to solve this. I know I'm getting a little bit redundant, sorry. Cosine 2x plus cosine 3x is equal to 0. All right, and this is one of my favorite tricks in math. What I'm going to do is I'm going to look at the average of my arguments, 2x and 3x. 2x and 3x. All right, the average of that is 5 halves, 2.5. All right, 5x over 2. I'm also going to look at not just the average of my two values, but the difference between the average and the values. So in other words, what is the difference between 5x over 2 and 2x? What is the difference between 3x and 5x over 2? And those two values should be the same because we found the average, so we're directly between them. So how far does this average deviate from my two values? And that'd be half x over 2. Right? 5x over 2 plus x over 2 is 3x, 6x over 2. 5x over 2 minus x over 2 is 2x. Right? So I have the average and then kind of like the deviation from the average. Right, I'm going to now decompose 2x into these two numbers. Cosine 5x over 2 minus x over 2. And I am going to decompose 3x into the sum of these two things. 5x over 2 plus x over 2 equals 0, of course. This is an equation. We are solving the equation. Think about what I might do from here. I have taken my 2x and I've broken it up into two angles. I've taken my 3x and I've broken it up into two angles. Using the double angle formula and the triple angle formula, essentially you're breaking 2x into two angles and 3x into two angles. But I've chosen my angles specifically, so something magical happens. Cosine, sine, sine. Cosine 5x over 2, cosine x over 2, cosine, sine 5x over 2, sine x over 2. That's my first angle, cosine 5x over 2 minus x over 2. You might already see what's happening. This minus became a plus, by the way. Cosine, sine. So cosine. Let me get this plus sign. Come on, Ben. Cosine. And I'm not going to use parentheses because I haven't been consistent. Cosine. Sine. Emphasize that minus sign has changed. Sine. Equals, of course, 0. All right. What happened? Cosine, sine. The signs cancel. Right, we have decomposed cosine 2x and cosine 3x in a way that gets rid of the signs. Cosine, sine. I'm going to be left with 2 cosine 5x over 2. Cosine x over 2. One of them, two of them, equals 0. And then now we've pretty much solved this problem. It's the zero product property. When is cosine 5x over 2 0? And when is cosine x over 2 0? Well, technically, when is 2 equal to 0? Never. When is cosine 5x over 2 equal to 0? And when is cosine x over 2 equal to 0? And we just need to solve those two questions and we're done. Right, we saved ourselves a lot of trouble. Right, so let's just finish it. 5x over 2. When is cosine 0? That is when the x coordinate is 0. That's going to be at pi over 2 and 3 pi over 2. Pi over 2 plus pi k. Same thing over here, actually. Let me fix that. X over 2 also can be pi over 2 plus pi k. Normally it's plus 2 pi k, by the way, everyone. But 0 is that special number in the period of cosine that happens multiple times in a perfect interval. Multiply by 2/5. The 2's are going to cancel. Pi over 5 plus 2 pi over 5k. And then we here multiply by 2. Pi plus 2 pi k. And I'm not sure if these are redundant or not. Pi, yeah, plus 4 pi over 5 is going to give us that pi. So I think this is redundant. It's just pi fifths plus 2 pi over 5k. Here is your answer. Not angry eyebrows, happy eyebrows. Boom. That is just another way to use the trig formulas that we've been learning in a more interesting way. Right? Once again, I want to emphasize that today's lesson is not about just more formulas in your brain. I'm about to give you some more formulas. But that's only for the people that want what we've just done in an explicit way. Right? The idea is that we have this basic tool, the cosine, cosine, sine, sine, sine. And it can be used in so many cool ways. Double angle formulas, half angle formulas, triple angle formulas, or averages and deviations. All right, I hope you love this as much as me, because the first time I saw this, I was like, are you kidding me? Why did I even bother? Anyways, okay. Let's jump down to kind of explicitly write these rules. So we're going to have something called the product to sum rules and the sum to product rules. And we actually just used the sum to product rule. Right? We used one of these new formulas. So I just want to emphasize that I'm about to give you a bunch of formulas, but they're very easily derivable. And in fact, I don't use the product to sum formulas. I kind of just do what I just did every time. Right, but they are derived pretty straightforwardly. Here, we're going to get the product formulas by, well, I'll give you a second to think about it. Maybe pause the video, look at what I've got here. It's been organized in a very specific way. What can you do to get a product of two trig functions to become a sum? All right, I'm going to go ahead and show you. I'm going to add these two things. If I add these two things, I'm going to get sine x plus y plus sine x minus y. Notice there's like some averages stuff happening here. That's kind of the essence of all of this. But if I add these two sides, I'm going to get 2 sine x cosine y. And these are going to cancel. Cosine x sine y, this is the essence. If these, I'm losing my words. We have the sum of two things turning into a product. This is kind of what we did before, right? The difference is the formula says take the product to sum, sine x cosine y, divide by 2 on both sides. That is sine x plus y plus sine x minus y divided by 2. That is our product to sum formula. So when someone says product to sum formula, that's what they're talking about. You have the sine of an angle times the cosine of an angle. Angles aren't the same necessarily. You can rewrite it as the sine of the two angles summed plus the sine of the two angles difference divided by 2. And then the next 4 just derive from that. So I'm going to do them real quick. This one right here. Let me make sure I'm not messing anything up. All right, so if I sum these, I'm just going to get what I just got. So this one comes from subtracting. All right, so if you have a sine times a cosine, you get that one in the beginning. If you have a, let's see what happens. We're going to get sine x plus y minus sine x minus y. Keep in mind, you could always like just flip-flop the order, pull out the plus, and use a different formula. We have many rules. If I'm subtracting these go away, and I'm going to be left with 2 cosine x sine y. And another one of our sum to product formulas, cosine x sine y is equal to sine x plus y minus sine x minus y divided by 2. Very similar formulas. Let me just make sure I didn't mess anything up. Nope. Cool. All right, here, I'm going to do the same thing. Well, not the same thing. I'm going to add these ones. Right, these are going to go away. This is going to be the product of cosines. The next one will be product of sines. This is a great time maybe to fast forward. Cosine x plus y plus cosine x minus y is equal to 2 cosine x cosine y. Yep. And then cosine x cosine y is equal to cosine x plus y plus cosine x minus y, all divided by 2. And for the finale, for the product to sum, subtract these two. This one's a little bit different because we're going to get a negative. Subtracting these go away. We're going to get a negative 2 sine x sine y. And we get divided by negative 2, we're going to get actually cosine x minus y minus cosine x plus y divided by 2. Right? This negative switches the order over here. All right, so there you go. There you have it. Those are our product to sum. We are taking the product of two sinusoids and turning it into the sum of two sinusoids. All right. I like the sum to product ones more because, solving equations. I'm a pre-calculus teacher. That's what I do. And solving equations usually revolves around turning it into the product of two things and then using the zero product property, that fundamental property. So the product to sum, decent. I like the sum to product. So here are the sum to product ones. This is kind of what we did in essence. So here are, on the page, the product to sum. We're deriving the sum to product. Okay. So, first step, let's go ahead and multiply by 2 on both sides. Sine x plus y plus sine x minus y is equal to 2 sine x cosine y, which is basically, let me scroll up. Well, not that. Circle the wrong thing. This thing. Well, actually, this thing. Right? 2 sine x cosine y is equal to the sum of x plus y and x minus y. 2 sine x cosine y is equal to the sum of sine x and the sum of x minus y. All right? What we need to do is turn this and this into a and b. Or some letter and some other letter. Some variable and some other variable. Because what we're going to be given is like sine of pi over 4 plus sine of, I don't know, x. Something. Right? We want to turn that into a product. We're going to have like a sine y plus a sine x, and we're going to want to turn that into a product. So that's our goal here. We want to turn x plus y and x minus y into separate variables. The problem is they're tied together because they're using the same variables. Let's do this. Let's call x plus y a, and let's call x minus y b. We have sine of a plus sine of b. What would that make x be? What is x in terms of a and b? Think about it for a second. We have a system of equations. A is x plus y, b is x minus y. What is x in terms of a and b? The way you do it is you do what we've been doing. Sum the two equations. Right? One of the many ways to solve systems of equations. We're going to get 2x is equal to a plus b. X is equal to a plus b divided by 2. Similarly, subtract the two equations. Sorry about the handwriting. A minus b is equal to, the x's will go away, that becomes 2y. Y is equal to a minus b divided by 2. And that is a cosine. Cosine a minus b divided by 2. right? Here is the formula that we previously used. Well, actually, technically not really, because I believe we used a third one here to solve our problem. We turned the sum of two cosines into the product of two cosines. Right there. We're going to be using this third one to solve that problem. We're going to be turning the sum of two cosines into the product of two cosines. That's exactly what this one's all about. Right here, we turn the sum of two sines into the product of a sine and a cosine. Here, we're going to turn the sum of the difference of two sines into the product of cosines and sines, etc. Okay, same thing though. We have established that x is a plus b over 2 and y is a minus b over 2. And we're going to do the same thing. Right, multiply by 2. Sine x plus y minus sine x minus y. That is equal to 2 cosine x sine y. Sine a minus sine b is equal to 2 cosine a plus b divided by 2 sine of a minus b divided by 2. Boom. Down here, this is the one we used at the beginning of the lesson, or midway through the lesson. 2 cosine x, let me do this the same way. Cosine x plus y plus cosine x minus y. 2 cosine x sine y. 2 cosine x cosine y. Cosine a plus cosine b is equal to 2 cosine a plus b divided by 2, the average plus the deviation, times the average minus the deviation. And then our last formula, I'm just going to go ahead and write it, because I can kind of see the gears turning. Same idea, multiply by 2, replace x and y. We're going to get cosine b. Notice that the x minus y is first. Remember that negative in the previous derivation on the previous page. Cosine a is equal to 2 sine a plus b divided by 2 sine a minus b divided by 2. Boom. The sum to product formulas. But really all we're doing is using that average plus deviation, average minus deviation trick. Expanding with sine, cosine, cosine, sine, cosine, cosine, sine, 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 and then some of the terms are going to chop and cancel. All right, we can use it right here. The sum of cosines is going to become cosine A plus cosine B. A is 2x, B is 3x. We're going to get cosine 2x plus cosine 3x is 2 cosine 2x plus 3x. And cosine 2x minus 3x equals 0. Right? That is the sum to product formula in action. All right, this is the problem that we solved at the top. Let's see if we get the same answer. We're going to get 5x over 2. That was one of them. And here we're not going to get the exact same thing. We're actually going to get cosine of negative x over 2. But don't forget, cosine is even. That negative doesn't really mean anything. Doesn't change our answer. All right, and then our final answer ends up being the same thing as it was before. 5x over 2 is equal to, we need to find out when cosine is 0. That's pi over 2 plus pi k. Over here, negative x over 2, pi over 2 plus pi k. Multiply by 2, multiply by 5/2, or 2/5, sorry, and we get our answers. X is equal to pi over 5 plus 2 over 5 pi k. And x is equal to in this case, negative pi. Yep, negative pi, but negative pi and pi are coterminal. Plus 2 pi k. Minus 2 pi k, actually, but I'll write that. Same thing, really. Doesn't really change anything. That k can be positive or negative. All right, here are your answers to the problem that we did at the beginning. Again, sorry for making you guys watch that twice. Solve that problem twice. But the idea is not to get a bunch of new formulas. The idea is to use what we've learned in a new, cool way. I hope you guys found, I know the formulas, that was a pretty boring part of the video. I will not disagree with that. But I hope that when we solved this problem, and also when we solved these two problems at the beginning, you were kind of wowed by that. And you're ready to use, or at least try to and learn to use what you already knew in a new way. That's the whole point. All right, I'm a broken record at this point. I'm going to close the video out. Have a good one, guys, and I will see you next time.